Okay, welcome to today's class. So today we'll be talking about algorithms and UML diagrams. I think Alec has given a short introduction to the part of the textbook, and I hope you read the textbook before the class. So today's class is basically as follows. We will start talking a little bit about how do we express algorithms using UML. Okay, that will be about 15 minutes, and that's in the teaching notes section 2, page 4. You will then have some time for looking at the general concepts, just filling in your book for some of the key symbols for UML diagrams. That will be on page 22 in the book. We will then start with an example of encoding an algorithm, the problem we just talked about for falling objects we introduced last week. We'll review the basic problem, and then I'll demonstrate how to draw the UML by hand, and then hopefully after that we will have our break. Following our break, we'll do the example of the optics ray tracing one. Again, in this case I will review the problem. I will then demo drawing the UML by hand. After that, we'll look at a numerical analysis and root finding. We'll review the problem. You will try to draw the UML. Okay? And then I will quickly demo drawing the UML. We will then hopefully have our next 10-minute break. Following that, we'll work on a rehearsal for milestone 2. So I'll give you an actual milestone from last year, and I'll give you a chance to work through it. It'll be an example, and we can try to help you as you work through it. And then after you work through it, you will work through it. I will demonstrate working through it together. And then finally, you can try milestone 2. Milestone 2, I hope we'll have a chance to do the first try for milestone 2, and then you will go home, I hope. Okay? So this is basically what we hope to do today. Is there any questions about that? Because I think everybody's pretty well past milestone 1, except for maybe one person who didn't attend any classes. So, okay, what's the definition of an algorithm? So I am now on page 4 in your workbook, page 4 in your book. So we're on page 4, teaching notes, section 2, page 4. So you know where we are, page 4. Okay. And this is the section we're going to be going through right now from page 4. Okay. The definition of an algorithm is a finite sequence of steps. In other words, there has to be some stopping condition. It can't go on forever. So a finite sequence of steps means it has to stop at some time. Each step consists of a few operations. Okay? And each operation must be rigorously defined and unambiguous. In other words, it's got to be very clear. There can't be two ways of interpreting it. There can only be one way to interpret each step. And secondly, we have to be able to execute it by a machine. Okay? That's basically this is a definition of the algorithm. So it's a number of steps. Each step consists of some operations to do, and each operation is rigorously defined and unambiguous and can be executed by a machine. If we can make this will be an algorithm. So now let's look at how do we diagram algorithms. We've talked about cluster diagrams in our Kuchi-Ingwen class and mind maps. We're going to go through this. So let's start. We're going to use an example problem to see how to do it. So here's a problem statement. I want to input an integer, and I want to get the absolute value of the integer. Okay, this is a very simple question, right? I'm going to input one integer. I'm going to calculate the absolute value. So for example, if I input 7, my algorithm should return 7. If I input minus 11, my algorithm should return 11, right? Because the absolute value of minus 11 is 11. Okay, that's Now, there are a few ways. Another way of representing is this sort of pseudocode, but this we are not going to work very much with, but I just want to show it for completeness. So I give the algorithm a name, get absolute, and brackets value. I would then put its purpose to take the absolute value. I then need to specify what is the input to my algorithm, which is one number or an integer. Okay? What is it going to give me? Is it going to change anything? No, it's not going to change anything. So we are okay on that. What's it going to return? The absolute value. And then we have the steps. Okay? Basically, we try to explain and in some sort of a level, you can see here, if the value is greater than 0, just return the value. Else, return minus value, and that's the end. So this would be basically how we would represent the algorithm in pseudocode. Our goal here is now to try to think about, unified modeling language. Okay? In unified modeling language, we basically have a number of symbols that we make use of. There's not that many. There's a start symbol, a transition symbol, an end symbol, okay? Activity symbol, which is something we're doing. This diamond, which is like either a branch, split, or merge. It can be used for decisions. A very thick line, which is called a fork or a join, which is used for parallel processing. And finally, we have comments. These will be in a square box with its corner cut off. Okay, you can see this box has rounded corners for activities. Okay, these are the only things you need to know for unified modeling language. We're not going to learn anything about object-oriented programming in this course, so you don't have to learn how to represent objects and things like that. For our course, this is all we need. Okay, so, for example, now here is the UML for the absolute value. There is my star symbol right here, and I've got a comment saying the input is an integer, v. Okay, I start here with the hard dot, I go down here and there's a branch. The flow changes. If the value of v, I think I should make a highlighter, right? Screen pointer options, let's make a laser pointer. Okay, so if v is greater than 0, I take this route, and then I join and continue, and I come to the end and return the absolute value of v. Okay, if this is not true, i.e. v greater than 0 is not true, then I will take this route. I will come here, I'll take the value, I'll put minus v, and then I'll just make it a negative v, and that will be positive. Like negative is a positive. So my now v this is going to be a positive number now. I will come down, I will join, and then I will return the v. So this is the UML diagram for our algorithm. Once we have our UML diagram, our next step will be to implement it in a language. For example, if I want to implement in assembler, for example, in assembler, a comment line, comments are started with a semicolon. So there's an assumption that it's an integer in 2's complement format, and r0 equals 0 is some assumptions coming in. So the first thing we do is inc r0, which puts a 1 in r0. We do a C-shift r0, 0. We load r1 from MEF, which is the keyboard. That's the number you want to take the absolute value. We do a bitwise AND. Actually, this checks the sign bit. R0 and R1, if it's true, then we know it's positive or negative. based on the value of R2, we will then jump to M09 if it's positive, which means we just save it, and we halt. Otherwise, we complete a not and an ink, and then save it and halt. Okay, so this is the way the computer is going to actually do it in terms of steps in assembler language. We generally do not, our course, we don't really care about this too much, but it's good to know. Okay? The same algorithm can be done in a few different languages. For example, here's the implementation in JavaScript. Okay, function, absolute value, if v is greater than 0, return plus v, semicolon, else return v, and there's a semicolon at the end. If we do it in Python, basically the comment is illustrated by these three. One way of doing a multi-line comment is the 3 quotation marks, and instead of function, it's just def. Okay, and there's a colon here rather than the 2 brackets. And then this. In ANSI, it looks almost the same, except integer, absolute value v. If v greater than 0, return plus v, else return minus v. Okay, and in each case, you can see these online comments are shown slightly different in each language. But it looks almost the same. A little bit of syntax difference, but not too much change. So let's now look at how we start to illustrate flow, and we'll start through. So basically, here the algorithm starts at the beginning and goes down to the end of the algorithm, which is here. Within the algorithm, we can have sequential operations or linear operations, decisions, that's conditional operations, or repetitions, i.e. loops, or parallel processing situations. Let's look at how we illustrate each of these now. So for sequence, the function starts from the very beginning and goes to the very end of the sequence. Each line basically executes once. It does not repeat. There's no repeating. It just starts at the beginning, goes ding, 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 ding. So anything we've done so far is probably going to be this way. We haven't talked too much about repetition yet. So the second type is decision. The function starts to run, and then based on the data, only part of the function is used, and the other part is not used for the data. So for example, here's our guy coming down. We'll wait for him to finish, and then we'll talk through him again. Okay, there we go. He starts down. He comes and makes a decision based on the data, and he chooses one way or the other. Choosing this way, he then does this step. Once he's finished doing that action, he continues on his way, joins back with the person that went the other route, and then continues on in the program. This is a conditional example. A second one, repetition or loops. The function starts to run, and each line is executed many times. Okay, so the function starts to run. Each loop is going to be executed many times. For example, 0 times, 2 times, 20 times, 1,000,000 times, based on the data. So we're coming in here. Okay, we would come down here. We would look based on the data. How many times do we need to run this? If this condition is not satisfied, we would immediately end and just skip the loop. Otherwise, we will come into the loop, do this activity, do whatever we're supposed to do, continue on, come back here, join in the condition, come back here, check again, is some condition satisfied, continue on, do the operation, and move around like this, and just keep rotating through the loop as long as some condition is not true. Once that condition is true, I can then get out of my loop and disappear. So that is repetition. The final one is parallel flow. These are tasks whose order is not important. So in other words, if I've got one computer core, I can do the two tasks in either order. Or if I have more than one core in my CPU, I can do two tasks at the same time. We will illustrate this, but we're not going to try to code it in this course. So let's go. I'll go back and so we'll try to see. Okay, so you can see how he comes here. Both routes are taken. So, and it doesn't matter which order you actually do these things. So it's not like, so you could do two things. It's like, okay. So two tasks can be done at the same time. And it doesn't really matter which order you ask. So it's, okay. So if we put it all together, we can see flow working some way like this. For example, we start here, we do a few linear flow operations, then there's a condition. I have to decide which route I want to go based on the data. I cannot take both. I will take one. I will make my condition, make a decision. Maybe I'll take this route and continue on, continue on, continue on, continue on. Oh, now I'm going to go and enter a loop and do something many times. Go around, do my loop a few times, and then I finish. Oh, I've done enough loops. I'll continue along on my processing. Oh, here's two things that can be done in either order. I can do this, but I have to do both. So I have to take both routes. So I have to do this, and I do this. So I will do both of these tasks in either order. Then I will continue on in my program and end my program. So we're trying to put everything together. Okay, I think that's basically summarized what we're trying to do here. Now I would like us to go, okay, please open your books now. We're going to move to another section of the book. Okay, we are now in this one. Please go to page 22 and just draw the key symbols for UML diagrams. Just fill in there, and TAs will just check to make sure you have them okay. And okay, you can just sort of give them the okay on that. Page 29. Pardon? Okay, whatever you have there. Okay. Yeah, I can remember putting those over. Probably somebody else put them out, maybe Answer or somebody borrowed it. Who knows? I don't know. Just okay. Okay, let's see, what am I trying to do? Okay. 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 Good. Good. Scan everything. Okay, good. Check. Okay, good. Okay, that's good. Remember your connector when you do the straight line, right? Okay, good. Oh, you know, I think. Okay, let's start it similar. Okay. There you go. What other one? We don't have any other one, do we?
Where we had to calculate 40.
Okay. Don't worry about today right now.
48. Yeah, and check. Can you check
Not done. Still not done. Okay, I'm saying completed.
Yeah. That's why I wrote it right.
Okay.
approaching something. The number is approaching.
Yes, it's okay. Yeah, that's okay. That one's okay.
There's supposed to be like one less than one greater than. Like this one.
That one's okay.
Eh? I think you got this one. 2.66 and 2.66 is greater than 1.64. It's supposed to be smaller and smaller and smaller.
Okay. All right.
How do I make this like the average?
Okay. Okay, yes, that is correct now. Yeah, it's very important you make sure you have that double dot in it. Or make make it, it's harder for people, if you only have one, people have trouble reading, they'll think it's
Okay.
repetition, right?
So,
So we're trying to make things clear.
So the average is
Okay, let's see.
I put the answer is possible. So it is and then when I put one,
Yeah.
I think here's a little mistake.
Oh,
There's no error.
oh, that's correct. You're right.
Yes.
Thank you, thank you. Okay, great. I got to make that change. Okay, great. Okay. Okay, great. Thank you. Connector arrow.
Because if I put it here 3 times 3 times 6 times 7 minus 10, it is greater than 0. And then after that, I add this it's 4
Okay.
divided by 6.
Okay.
Plus 1 is 4 divided by 2 is 2, right? And then
That's,
I think
okay. Okay, let's continue on. Okay, what we're looking at now, I'm going to download, and then we're going to start looking at our example for gravity, will be our next one to look at. But first I want to download so you can see. From here I'm going to use this guy, Blackboard Toolbox, just so I can demonstrate. So you basically, and for you guys, okay, we'll enable editing, and where you guys should be right now will be, okay, I'm going to try to move us to, where's our guy? Okay, so you'll be moving on to section gravity number 2, page 29 now. If you can open your books to page 29, and I'll review the problem, and then I'll start drawing, and then you can draw the UML as I also draw the UML, so that we both can move along at similar pace in doing our first UML for this problem. Okay, I think I got this thing working. Good. Okay, I don't have to hold this anymore. All right, so that's what we'll, okay. So if you recall the problem, we have falling object. We are determining mathematical equations, and basically we have our dropped object. It fell from the roof, we've calculated time, and we basically have some sort of a table like this. We took the data, for a light object, and we found that we can calculate velocity and acceleration using these formulas in the literature, and we also need to calculate the mean time. We then use this and slowly filled out this table, quite repetitively, right? Take these by this minus this to give us the velocity. The average of these two is the time. We then took this minus this divided by this minus this to give us a velocity, and we took the average of this to get the time. Hey guys, problem, question? If question, okay, can ask. Yeah. What? If you have a question, probably other people have a question too. Yeah. Okay. Yeah. Wrong? Yeah. Okay, what's confusing? It's only confusing is fast. I can, okay, yeah. You understand? Okay, alright, okay. Try it. Okay. Okay. Yeah, okay. Don't want people to get sort of behind or lost. Okay, so we did these manual calculations, and for acceleration we took this velocity minus this velocity over this time minus this time, and then got this acceleration, and then we took the average of these two times. And then we repeated to fill out our table. Okay, so now we want to generate a solution, so we need to go to UML to do that. Okay, and that's what I'm going to start to work on now, and we're going to work here on the Blackboard. Okay, this is what I just downloaded so I can show you what I'm doing easier. Okay, so I'm going to want to start my routine. So I'm going to take this one, Control D, give me a copy of it. And then I'm going to need a transition. So I'll use him just to draw my nice transition. So you can also do the same thing with yours. And then we have some actions to do. What was the first action that we need to do? Is basically to, well, we have to, if I look at where we did the problem, the first thing we want to do is to input maybe x1 or h1 and t1. I wish this didn't, okay, my h was small, so whatever, h1 and t1. After that, I'm going to also want to, next step, I need to input the next set, right? If I remember what I did on my, where's my problem again? Where did I go? Okay, you see how, so I input h1 and t1, and I'm going to input next h2 and t2. That's the next other piece of information I want. So I'm trying to generalize this. So I'm just going to copy this. CV. So I'm going to input the second number h. Okay. Oops. That's T2. Okay. Once I've input that, what else did I want to do? The other actions I need to do is, let's look at the actions from my script, from my thing. I'll go back to my thing. I need to calculate T average, T2 plus T1 over 2. Okay, I can put that into this box. TA equals T1 plus T2 brackets divided by 2. Maybe I'm going to need it on 2 lines. Okay, T average. Okay, so that's one thing I'm wanting to calculate. And from my working on this guy, I also need to calculate this H2 minus H1 over T2 minus T1 to get my velocity. Okay, so I'm going to maybe, or acceleration. So I'll probably get another activity to do. So maybe D equals, well, H2 minus H1 divided by brackets T2 minus T1. Okay. And then after I do that, I need to then print the 2 results, right? I need to print output V and T, because I've calculated both those things now. So I'm going to output. That will be another action I want to do. Output TA, or let's say D and TA. Okay? And if I'm doing, okay, I probably put an arrow here to say there's a transition. Now, I need to think now. I need to calculate T and V. Looking at these 2 equations, does it matter which order I do them? Does the order matter? No, it doesn't. Okay, so I can then make them as a parallel process. So I can put them there. I will put, but I do have to calculate them before I print. I can't print them before calculating, so that has to be later. So I can maybe make D. I'll copy this guy. Copy this guy. So I illustrate this calculation can sit here, they're in parallel nicely. How come this arrow is longer than the other one? I don't know why. But anyways, okay, I'll try to make them nicer, neater. Okay, that's better, I think, hopefully. Move him up a little bit so he's touching, okay. And I'm going to want I'll move him down just so I have to have a second. If I'm doing a parallel bar, I have to put another bar when the parallel process ends. So my parallel process is going to end here. So I have my two arrows showing what I'm doing next, and then the end of my parallel process. Okay, and then after that I output. And finally, I could say, okay, I could then stop my program, which would be this guy. And here we are. Program is basically stopped. Okay, so in this way, so I input H1 and T1, input H2 and T2, I calculate TA, I calculate D, and then I output D and TA. So in other words, I just done one. But the neat thing about this is the same process I'm going to have to do for the next two set, and the next two set, and the next two set, and the next two set to get all these guys. So this is actually a loop, right? It's not, I'm going to keep repeating this. So I can now illustrate what I want to do is I'm going to have to repeat this. I don't want to stop here. I'm going to want to calculate the next two. Now, I can notice that for the first calculation, let's look at this chart now. For the first calculation, this is this is H2, this was H1. For my next calculation, H2 is going to be equal to H1, right? And this is going to be H2, this is going to be H1. This was T2 in my previous one. It's now going to be T1 when I do my next calculation. Okay, right? So, since I've already input it, the next thing I'm going to want to do is a simple action here. Let's switch this arrow, so I'm not going to go down here to the let's go this way instead. Doesn't really matter as long as they're connected. Okay. I'm just going to make H1 equals H2. Take the value that's in H2, put it into H1. Take the value that's in container T2, put it into container T1. Okay? And after that, I'm going to have to input this guy again. Let's say maybe I'll just move him here. And move this guy over here a bit. There, he's nice. Okay, since I've already connected these guys, let's connect him to here. Make him a connector to here. Okay. I will now input the new H2 and T2. And there's got to be a decision here, right? Because I'm going to keep doing this, but it's got to have some time to stop, right? So I have to have some sort of stop condition. So maybe H2, T2 is no more data, okay? Probably no more data could be one stop condition. So I'm going to do that. I'll move my D. Okay, he will come to here. Good. This guy will come to here. Yay. Okay, and I'm going to want an arrow going across. Let's move him. Let's take him and put him to here. Okay, and probably I just want a simple message on this one. I could use a comment, or I can just put a little, actually let's use a comment here instead of the, okay, escape, I can use comment. Let's use comment this time. Control Z, 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 okay, comment. More data. Okay, I'll put my comment stuck up in here. I'm sort of crowded. Okay, let's move this thing over. Isn't it wonderful? On a computer I can just move everything all over the place when I run out of room. You guys can't, sorry. Okay, he connects to here. He connects to here, more data, and I can just put a little note. Let's shoot him up here, and I'll pick a little note. Yes. And it means if it's yes, I will take this route. If it's no, I'm going to have to give another route to take. Okay, there's my arrow. No. If it's no, I'm just going to go to the end of the program, right? I'm just going to go to the end. Where can you snap? Is there a place you can snap on here? Here we are, nice spot to snap. Okay, good. All right, so I've now created the UML for calculating all my velocities, right? I can just now go through circle through this, and when I run out of data, my program has stopped, and I will have been able to fill in this table completely. Okay? Now I could just, as you can see when I do the acceleration, it's the same calculation, so I can use the exact same program to when I have the velocity and time to calculate the acceleration and the time. Okay? So I could use the same program. I can run the program twice. One time to calculate the velocities, one time to calculate time. So there would be basically my final UML for the first case. We will now break for 10 minutes, and if you have questions, I know actually you can have the TA stamp and then take your break, okay? Have your TA stamp your UML at the corner of the UML, and then we'll continue on, okay, after the break on another example. Okay, so it's now break time. And I think I should, okay, let's stop recording. Okay. All right, so we're going to go to page 37 in your book. Optics, section 2, page 37, optical ray tracing. Let's quickly review, and then we'll demo the UML by hand again. Okay, so let's get, okay, so optics, there we go. Optical ray tracing, the simulation. Okay, remember the problem? Our problem is basically we're going to try, in the long term, we want to determine the location and size of a final image formed by an imaging system composed of multiple lenses. In other words, there's not just not just one lens, but a whole bunch. And I think okay, so we have this sort of a, remember the optics, the optical rays shoot out, they come back and they condense, and we want to find where the actual image is going to be. So, for example, if we've got an object here, we put our CCD right here, we'll be able to image the person right at this point. Okay, at this point, sorry. Okay, first of all, we decided we'll do a problem with a single lens. So we have a lens stuck here. It is a focal length F. We're offset by a distance O on one side, and we want to see how far the image is on the other side and its height. And we know our initial object's height. If we do our literature search, we find this simple formula, 1 over O plus 1 over I equals 1 over F. And we can rewrite the n, we find the magnification equals minus I over O. So if we know I and O, we can get the magnification. So, moving ahead, we can then rewrite this so it's an equation. I equals OF, O minus F, and H equals HO equals I over O, H image equals I over O, HO. Okay? The image. Once we've done our literature search, we did a bunch of hand calculations, and you drew the pictures last week. Now we're at the point of generalizing the solution to using UML. Okay, so that's what I want to do now. Let's pull down and get back to our Blackboard again. Where did my Blackboard downloads? Okay, move my Blackboard across. Okay, here we are. Okay, so what have I got here for my other okay, there's two calculations I'm going to be doing. Let's just I'm just going to copy some of the stuff from the previous one, Control C. I'll put them over here for reference. This is not part of my UML. but this will just put them over here. These are the two equations. Okay, so my program is going to start. My function is going to start. I will probably then, okay, I need a transition symbol to go to my first object. And what is the first thing I'm going to have to do? I'm probably going to need to input. I will probably want to input the object. I want to know the object height, and I need to know its distance from the lens. So O. I'm going to need to know that information about the object. Okay, that's about, and I'm also going to need to know I'm going to have to input so this will be input. Okay, I should probably write input, sorry. Input object H and O. I'm also going to need to input lens focal length. Okay, so maybe I can do those. Now, this, I guess I'm going to do it this way. It doesn't really matter. I could put this as a parallel process too, so I could write it this way. Input lens. What do I want to do next? Okay, is order important? Yes, it is. I can't calculate H unless I know what I is. Okay, so in other words, I've got to do that one first. I cannot do parallel here. This has to be a sequential object. I have to first calculate I equals OF divided by O minus F. Okay, and then after I know that, my next step could be to another action. So once I've calculated I could then calculate H out, the H out. H image equals minus I divided by O times that big H that I have at the very beginning, H, which was my H of the object. Okay, so that will provide that. And if I've done my calculation, then I probably have to, I guess my next step will be just to output H I comma I. And I'll need my little arrow here for that. And oops, not way down there. Okay, and then I guess that finishes the calculation for my lens, right? I've inputted the object, HO, I've input the lens F, I've done my first calculation, I did a second calculation, and then I output stuff. Okay, so there's my UML. There's a UML I just drew. Let's move this UML over here and think if there's other ways we could do this. Okay, now a UML is not necessarily, I could look at these the same and say, well, maybe I don't want to write it this way. I could also write something different. Let's try something. I'll copy these guys again. Okay, move them over here and say, oh, okay. I could put in the lens at the same, there's no order here, so maybe I can do it this way in parallel, right? I could do it in parallel if I wanted to do the inputs in parallel, right? I could do it this way and then D, grab this guy, grab his partner. So you don't have to write this down. I'm just showing that we can put them either way. This would be another way we could do it. Input this. Okay. Okay, and then jam this down here. So this would also be correct. So both these, I can get rid of these equations now, but either of these UMLs would be correct. There's no problem with either of them. Okay? This one just emphasizes the fact that it doesn't matter whether you input the lens information first or the object information first. Okay? This one, okay, we just do it nicely sequential ones, no loops, nothing. It's very simple, straightforward. Okay? If there's, I will give you a couple minutes to make sure, try to understand it. If you have any questions, please ask the TAs. The TAs can give you answers to the questions. Okay? Or we'll just walk around. If you have any questions, please ask Alec or ask Rahim or myself about this UML, and then we'll start our next UML in about 4 minutes. Okay? 4 minutes, we'll move on to the root finding one. Okay? So just go along and we'll look at your work and see if it looks okay. Okay. They have to be the shape. They can't be the shape. The shape is not correct. They have to be, they need to be, okay? But it's a factor. Correct shape. This is a routine. This shape, this shape. If you click on this thing in PowerPoint, you'll see a whole bunch of different but we're only on, these are the only ones we want to use. 80% of programs. But the whole structure here, PowerPoint will be the only PowerPoint. Okay? No? I didn't give you a template. The reason we want to do that is this shape is for and if you look at powerful like this here, a lot of UML okay? Just be careful. Okay. Okay, got to do more than that. Okay. Right now, no more templates. Yeah. Okay. 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 All right. Okay. That's. Okay, we're going to now move on to numerical analysis. Numerical analysis will be the next one we'll be looking at. So if I go to, okay, let's remember that guy. Okay, root finding for p, like the square root of p or the cube root of p, etc. And, okay, we first of all start with our problem. We want to calculate the root of p. And we looked at trying to develop our algorithm. So we ended up with fx equals x squared minus 2. And we want to make this thing go to 0. And we want to solve for x. If we know what, if we can solve this, if we can send y to 0, we will know what x is. And we looked at, this is the curve of x squared minus 2, y equals x squared minus 2, the curve, if I want to plot it. So I can take a few guesses. First I tried, we know that 2 is going to be too big. The square root of 2 is definitely less than 2, and it's definitely greater than 1. So I try both of these, and I find that, oh, okay, if I substitute in x equals 1, I will get a negative number. If I substitute x equals 2, I will get a large positive number. I know the root is halfway between the two. So x equals 2, I sub in, and I find out, 2, if I put x equals 1, I will get a negative number. Okay, so I know the root has to be between here and here. So I take a number halfway between the two, substitute in, it's positive, so I know the root has to be between here and here. I then put in go another root halfway between, and I find, it's got to be here, somewhere between here and here. I take another one halfway between, and I'm getting closer and closer each time. I know this is the interval. Okay, we observed that we needed two starting points, a big number and a small number, and we try to use 2 and 1 to start. And we know that it's going to be somewhere between there, and we just kept taking the median. So now we need to generalize the solution to XML, which you are going to try to do by yourself first. Okay, you try first. On page 49, start to fill in your UML diagram on page 49. You try to solve the UML, and then I will try to demo by hand at about maybe at around 5 minutes to 4, okay, or 10 to 4. Seeing how people do, by close to 4 o'clock, we'll try to work through together. But first, I want you to try it, page 49, try to draw your UML diagram, okay, and for this problem, okay, so there's you can remember how you did your solution. Now work on trying to draw the UML diagram. Okay, and the TAs will try to help you as they go by.
I can keep the money?
Yeah, keep the money. Keep the money in your pocket. Pardon? Jenna. Okay, great. Okay. Well, no, you can't keep the money, but you can deliver it to the print shop.
I can put it in my keeping.
Yeah. Okay. So okay, so you're on page. Oh, bother, some people not quite sure what page they're on, okay?
49.
Page 49, okay guys, 49.
Professor,
Yeah.
I wrong the wrong building.
Okay.
Sorry.
Okay, no problem. Okay, so now we're helping the students do UMLs for root finding equation. Okay, so just try to help them as they try to work on their UMLs. Okay? Okay, if they have problems, we'll talk to them. Okay, great. Okay. I wondered what happened to you. Okay. See what?
They want to see the PowerPoint.
Okay, PowerPoint. Yeah, that I'm trying to. So I wanted to have them find. Okay. There you go, okay. Oops, sorry. What did I do? Water.
I have one. I have a copy here, right? Yeah. So right here, what we're working on, right, page 49. Actually, I was trying to copy it and copy 83 rather than that regular size 40. Sorry about that. So yeah. There's the this one. So we're working on this guy right now. Okay. So.
You can also check it, see the Japanese is Alex Japanese. You know, okay, good. All right, good. And you will write it. Okay. Not really. We don't. We have to do it. You only calculate what we calculate. We only put it right. We put the try x. We put an x one. We put an x b. An x s. Right. We put an x b. We put an x s.
Any other number square root of 1, right? Smaller than
Okay. You don't want to input a y, right? We never input y, right? We input x, right? Correct? Right? We input the x, good. And then what do? We calculate. Don't we do the calculation next? Well, yeah, when you do the calculation, you have to write the calculation, right? Y equals x squared minus 2. And then you say, is y greater than 0 or less than 0? It's going to determine what you want to do, right? Okay, how's your stuff doing? Express, okay, calculate, okay.
I'm stuck in here.
Okay, fair enough. Okay, it's sort of. Okay. You got the idea, kind of, yes. Okay.
I'm not done yet, actually.
Okay, looks good, okay. X is okay. Y, okay, fair enough. Y less than 3. Okay, that looks good. Go together, come back. Okay, alright. This is okay except for the fact that, okay, that's correct, but this is not going to be here. It can go into here. The diamond only has you can't have so many inputs into the diamond. Something like that. That looks good, that's good, that's correct. The logic looks reasonable. Okay, good. That logic is reasonable. Okay, good. Alright, good. Alright, you're okay, good. Next day, okay, good. Hopefully, what's the VW? Oh, I must be assume it's okay. But where you have to calculate this somewhere. Think of where you want to calculate. Huh? Yes. There's something missing. Where are you doing this calculation? That calculation has to be done somewhere, right? Okay. before you do the one after another, it doesn't matter. You can just, yeah, this is a, or, yeah, correct. You can just, yeah, right. Or you have to do an XP and it says, one B equals equal, but then in this one, we need to change XB or XS, right? Basically three numbers, right? XB, XS, that's why I put X goes with the correction. So we probably need to calculate this first by doing the X big plus X small. There's two numbers, right? XS and XB. And then you try to put your number halfway between the two, right? So you have to find the number halfway between X, Y, XB. Then you do the calculation. Then you can decide who you want to replace XB and XS. Okay? Is thinking. This is important part. Logical thinking is very important. Because we're going to code, we have to make sure we know what we want to do. Okay. And you have that UML diagram. You can also check. But if you can't do that, you can't do it. Then you have to calculate this, and then you do this calculation. Then you make the so order is slightly mixed up. But ideas are okay. Order. Okay.
The pen.
Okay. Okay, let's slowly walk through it together now. I think we'll try to walk through it a little bit together, if that's okay with you guys. Let's start to walk through. I hope I can get rid of this ribbon. Okay, this should be big enough on your screen so we can see what we're doing a little bit too. Okay, first of all, we have a few actions we have to do, right? One of the actions is going to be this equation. So I would first of all put this box on for my action to do. Hey guys, you okay? Can we listen please? Thank you. So one action we have to do is y equals x times x minus 2. We need to do this calculation. You can see we're doing that calculation many times here, right? We do that calculation. We do that calculation. Another calculation we do, oh sorry, this sort of shouldn't teach that, is we also have to calculate x's, right? And each time we do that, we take the number xs plus xb over 2. So, x equals xs plus xb divided by 2. Okay, so these are the two actions that we are actually doing in this thing. We're calculating the number between, and then based on, and then we put that in, and we actually calculate. So I'm going to connect it. Once I know what x is, I then calculate y equals x squared minus 2. So at the very beginning, what did we input? Okay, I better get my thing started now. So what did we start by doing? Here we start by inputting one number that's too big and one number that's too small. In other words, we input xb equals 2, xs equals 1. So we basically input xs, a number that's too small, and an xb, a number that's too big. Right? That's what we first input. That was our first step, was inputting these guys. So we input a number that's too big and too small. So we know the square root is somewhere between xs and xb. We then calculated a number here. So okay, our next step after that was to do this calculation to find another value of x to test. Right, we calculated number halfway between, and then we calculated y. Y equals x squared minus 2. Now, from this number, you can see here what we did. Is it less than 0 or is it bigger than 0? If that number was, we then had a decision based on the value of y. So in this case, I would say, okay, we're deciding. We can have two possibilities. Y could be greater than 0, or y could be less than 0. So I then have a decision split here. Let's assume that I need to, come on, let's get you, come on, connect. There we go. Okay, I'll shoot my thing out here. Let's assume that I'm just going to put a little note there so I remember what I'm doing. Let's assume that y is greater than 0. If y is greater than 0, what does that mean? If y is greater than 0, that means, looking at my graph, if I got a y greater than 0, that means my number is too big, right? If y is greater than my number is too big, so x is too big. Therefore, all I want to do is, I can then say, okay, I know x is too big. If y is greater than 0, then x is too big. That means xb equals x. I can take the value of x and make it now the too big number. Okay, so I've got that. On the other hand, what happened? Let's take this arrow again and swing around to this side. If that's not true, i.e. now y is less than 0, I don't have to write that because if y is not greater than 0, it must be less than 0 or equal to 0. If y is less than 0, that means my value of x is too small. So I can replace my previous small x, s will now be equal to x. Okay? So I've done either one or the other. Once I've done this according to our format for USB, for my thing is, I can now combine the two. I've made my change. I now need to combine them. Okay, let's get them combined. I'll just do snap, snap, the snap, snap. Okay, so now they're continuing together. Now what might I want to do? I can probably, at this point, I probably want to, why don't I just print out, this doesn't really have to do it now, but I could do this. I think I would like to do it right here. Maybe I can just output xs comma xb. All right, and I can now decide: am I happy with XS or XB? I've got to decide that. So probably I'm going to need a decision here to see if I'm going to stop, right? Let's see if I'm going to take some sort of a number. Remember, we're talking about how close we are. So maybe I can put here a condition. Where did my condition go? If XB minus XS is less than 0.01, I say that's close enough. I don't want to be closer than that. I'll make that condition. If this is true, then I'm going to stop. So I'll put my arrow over here. If that's true, I want to stop. If it's not true, I'm going to have to continue. So let me think. How am I going to? I got to figure out where I want to go now. So first, I'm going to take an arrow here. Get one of these lines. Get it out of here. Okay, let's move somewhere. Where do I want to go? Probably I need to go halfway between the two, right? So I think I'm going to jump into here. Let's see, how can I get over there easily? Not that easy with my way I've got my arrows. Maybe I can make a few of these guys, make it more neater. Another guy, send him across to here. And then we'll go back up to so I'm going to come right back in here, I think. So I'm going to then take another x that's halfway between the two. I'm going to calculate what y is. If y is greater than 0, I will make the small one or the big one, and I'll take which root. Then I will join back together again. I will output my next two, xs and xb. Okay, so let's try this for our example here with our root true to see if this is actually a correct UML. I'm going to move it over here so I can see what I'm doing. Okay, there's my UML. Is this an accurate description of what I was actually doing? Okay, I started with x2, which was too big. Okay, so I'm inputting 2, inputted 1. 1 and 2. I calculate. I try x equals 1.5. Okay, that was 2 plus 1 is 3 divided by 2 is 1.5. I did that calculation and found that y is greater than 0. Therefore, I set xb as equal to 1.5, and I output xs and xb, which was 1, comma, 1.5. Okay, up to here, okay. I next go along here, I come up here, I try to add them together. 1 plus 1.5 divided by 2 equals 1.3. Okay, to one significant figure, 1.3. Okay, I do the calculation. I find that y is a negative number. Since now y is less than 0, I take this root and let xs equal x. X being 1.3. Now xs is now going to be 1.3. So now 1.3 is less than root 2. And I output these two numbers, 1.3 and 1.5. Okay, xb minus sx is not less than 0.01, so I would keep going. And, okay, 1.3 plus 1.5 is 1.4. Okay, 1.4, I do the multiplication. Again, 1.4 squared minus 2 gives me minus 0.4. So now my xs is 1.4. I come back, I join again, I output 1.4 and 1.5, and in my example here I said that was close enough. Okay, 0.01, maybe I'll change my, just a second, I'm going to change my condition here to make it 0.1, there. So now I meet my condition and I can stop my routine. Okay, so this will be the are there any questions here? Maybe that, Okay, me and the TA will walk around for about a minute. We're going to take a 10-minute break now. We're a little bit late or slower, but we'll take a 10-minute break. And if you have any questions, please ask the TAs during the 10-minute break, and we'll come back and do some more work on UMLs after the break. Okay. Okay, let's come back. Hi. Okay. Great. Okay, so let's quickly review this, what we just did. We've worked through this guy and how we move slowly through. We can then create our UML to try to explain it. So when we generalize the solution to the UML is our first major step. So the inputs, in this case, I'm inputting two things. In general, if I want the square root of p, I have to input the number I want the square root of. And I need to input epsilon. Okay? Okay, this would be it's another activity diagram. This is slightly different from what I just gave you, but it also is okay. What number do I want the square root of? And how accurate do I want the square root of? That would be the epsilon. I can then make my small number xs equals 1, xpb equals p. Why do I want to do this? Because I know that any root will be in the range 1 less than x less than p. And we can use these limits as our first guess. Okay? So once we have this as our first guess, we can then start with our program. We check. Come on. Okay? We want to stop. We first have to check. If my guess is close enough, xb minus xs is greater than epsilon, I'm going to continue. But if I'm close enough, I want to stop. And I'm going to output xs and xp. So for example, if I say I want the square root of 1, okay? That would be an example. So I'd input 1 and I want it to 0.001 accuracy. My first guess, xs is 1. My first guess for xb is 1. So obviously I don't have to do anything. xb minus xs is 0. So that means I can just finish and output that the square root of 1 is 1. I don't have to calculate anything. Okay? But in the case of like the square root of 2, I input 1 and 2. It's going to still be too big. So then I will have to enter into my loop. Within my loop, I first half the range to make my first guess. xs plus xb over 2. Okay? I will need to half my guess. To do my guess, I'm going to guess halfway between the two. I calculate. Oh, I solve for y. What is x squared minus p? If x squared minus p, is it less than 0? If it's less than 0, then x is too small. So I can put the value of x into the container xs. If y is greater than 0, in other words, say 6 squared minus 2, I know that 6 is too big, right? It's a positive number. 6 is too big, so I can say, okay, xb is now 6. Okay, and then I will continue on. I'll find they're too big, and I'll just keep looping through here, taking the numbers halfway between the two, and slowly working my way down. And then finally, when I'm close enough, I will output xs, xb. So this would be, this is a bisection method for calculating the square root. There are a few other methods that may be slightly faster, but this is very reliable and will not break. Okay, so there's our UML activity diagram, and this thing is always, is it close enough? Now, note, if our UML is wrong, our program logic will be wrong, and we're going to waste our time doing coding. So the UML needs to be correct. If it's not correct, our programming is just a waste of time. Writing code because our UML is wrong and it's not making the correct ideas, and you'll spend lots of time coding and you'll never get the right answer. It'll never work, your code, just because your UML is wrong. Okay, so that's basically what we want to do for UML activity diagrams. Now, we're going to work through a sample milestone. You're going to have about, again, about 25, it looks like we're going to give about 15 minutes for you to work through this milestone and see how you can do on it, and then we'll work together and I'll try to show you how I would do it. Okay? So this is just for practice. We won't be using this for counting as a milestone, but this will be practice. Okay? All right, and it looks like, depending on our time, we will do the next, we'll do the real milestone 2, maybe at the beginning of class next week. I'm not sure. Okay? We'll see how that works. Okay? How our time is. Okay, let's, so, our time, if I get to my, where's mine? Okay, so we're now doing making muffins. Yes, a traditional, a happy Canadian food that we like to eat a lot. And what? Oh, waffles. Sorry, waffles. My mistake. Waffles. Oh, we're doing waffles. Okay. Sorry, waffles. Waffles, not muffins. Waffles. Sorry, waffles. Okay.
mean.
Okay. Okay.
Pardon? The what?
What the one that you showed us?
Where?
Picture?
This one. Oh, it's not there. It's not on, no. You just finished copying it, right? So this is you're going to be doing on the back of this, right? And you have your notes to look at, right? And you've done examples here in the notebook, yeah. Here it is, you kind of paste on that.
There's one more thing that you can do in this part. One thing you can do. Mixing the triangle.
Ideally,
You can this first, you can do this every problem you can do one by one, but you have to make the test.
things should be, these are definitely, these are not just, these are definitely not, single statements, when this happens. That's an if, right? This is supposed to if, and those are loops you have to wait for, right? It's something to do with anything you want. Yeah. Ideally, they do the word, but the number's okay. The number is okay for practice, yes. For practice, it's okay just to type the number. Okay? In the test, they would want to write down what they're doing, yes. But here, writing the numbers is okay because they're trying to get the idea how to do it. Okay, so just writing the numbers is okay. Okay.
Near the park. There's a walking place. You guys all go and try that. It's really good. And they have strawberry walking. And the best thing is that you can have half of walking. Better than you take a photo and then you can read. What is my name?
There's no two places. How can there be decision?
Say the right and
Where do you go from the wait state? You're stuck in the wait state. There's no arrow going out. I'm going to be waiting forever. I'm never going to.
No, there's no yes.
What? When I get, yeah, so I get to here and I can't go anywhere. I'm stuck. There's no exit. I'm waiting forever.
Wait.
I'm waiting forever there. Unless I'm going somewhere. Here, I'm stuck here too. I'm in a wait state. I'll get stuck here. I can't get out. Okay. Okay. No. No. Because when we put this thing here, put this here, so that everybody's circle inside. But it can't be axed. It cannot be jumping. But then I'm never checking to see if it's for the batter. Light goes off. When light is, no.
Oh, there's supposed to be one.
This is so confusing. What am I doing shooting? Why am I going way back here?
If you want another one.
Okay, alright, okay, but okay. Alright, okay, got my, okay. First, okay, now, a few things. This arrow cannot go in here, it can go into here. It can't join there. It's got to join here. And this wait, when the light turns off, is the light off? No. I wait a second, then even the light's still off. The lights never turns off when I pour the batter. So this should be, this is not an action to do. This is not an action. Light off. No. Then we go wait and then come back into here. Yes, pour batter, so you're going to loop right in here. But this is not an act. Waiting is not an act. This is not an action. So you're not doing anything, right? This is a condition. So it should be a comment. Stop. Yes. Okay, so it's not a no. Then you got to come back here again, yeah, and do the check again. Okay. Yeah, that's good. Yeah, that's okay. Yeah, okay. Okay. No, you're dying. You're stuck in the wait state. Yeah, you can come. Maybe you know your phone. Yeah, go there. We already know what we don't want to go right there. Yeah. Okay. No, there's no decisions up here yet. There's no decisions coming. You're just doing things right now. Decisions don't come yet. But we'll now start to walk through it. Okay. Yes.
You'll collect the paper?
Yes, you can give to Raheem or Alex or something, and we will discuss.
Show me UML.
Okay, guys, let's, we're gonna walk through now. Okay? We'll just walk through what we've been doing, and I think this is, open mic is on. Okay, we'll walk through, the waffle guy, house problem. Let's walk through it so I give it, again, my solution is not necessarily the best, but it's one solution, okay? All right, so let's get started, and the way I would start to work on it. Okay, I probably start with a comment, ingredients. Okay, I'm going to start with, I'll start my process, and I'm going to start with an assumption that all my ingredients are available. Okay, I'm going to assume that I've got all the ingredients available, and then I can start to, I would then probably start to throw my actions down. So for example, my action of mix dry. I've also got what else am I doing? Step 2 is a separation of egg, separate egg. Separate egg. Separate eggs. Eggs, okay. I got to separate eggs, and then I've got to beat the, okay, I've got to beat the eggs, okay. So that's going to be right after beat eggs. Beat egg whites, right? I think that's what I'm doing here. I'm beating the egg whites, and I'm also wanting to mix the wet ingredients. Okay, so I can say I can mix wet ingredients. Mix wet ingredients. What other things do I have to do as I go down here? Okay, let's get started then. Okay, so I'm going to start. I can do some things in parallel, so I might get started with parallel stuff. If I'm looking at what I want to do, I can probably mix the dry ingredients. It doesn't really, and mixing the wet ingredients are okay, but I've got to separate the eggs first before I can mix the wet ingredients. So I'm probably going to put this right into here, right? If I'm organizing for my parallel. Here's my little arrow coming down. My parallel guy. I'm mixing the dry ingredients and separating the egg yolks and mixing the wet ingredients. Mix dry. Separate egg yolks have to be done before I can mix the wet ingredients. So this has to be done first. Okay, next things, okay, then I want to combine the wet and dry ingredients into a large bowl. Okay, okay, I'm gonna this can go all the way down here, I guess. This guy will go to, okay, this guy will come down, mix wet, and then I'm going to mix all these guys into dry. Okay, probably up. I will, okay, and then I'm going to mix all, combine, okay. Combine, probably I'm going to do, I can do that here. And I could also, at the same time as I'm combining, I could also be beating my egg whites at the same time if I want to, right? These guys can both be done at the same time. There's no real connection between the two, so I would maybe want to do that. Let's get another one of these guys. Maybe I'll copy this whole thing. Down here. And okay, once I've beaten the egg whites and combined all the dry and wet ingredients, I guess I need to join them together again. Where did my thing go? I don't want a slideshow. Okay, I'll probably link them together. I'm running out of room. Okay, so these guys are linked, hopefully stuck here. I'm gonna have to move this thing up a bit. Sorry. Whoosh. Move him over here. Range order to front, bring to front. Okay, good. Okay. He's happy there. Okay. He's now up here. Okay, I beat the egg whites. Next I'm going to fold is the next step. Fold, okay, fold. Okay, let's get my arrow out of here. I gotta go to a nice high spot again so I can start again. I'll shoot across to here. I'm going to do my folding. Fold into batter. Okay, heating up waffle iron. Oh, okay, that could also be done in parallel too. I don't need it. It can be done way over here. Okay, I can put him over here. I'll extend this guy. Heat, because there's no requirement to do any of this mixing first, so I probably heat first should be a good idea. Okay, so he doesn't have any preconditions. So I would probably put him here. And I've got to check to see when light warms up, pour batter on iron. Okay. I'll put a loop here. And maybe a comment. Light off. Light off. Okay, there's my comment, and I'm going to get my comment bar. Okay, if my light is off. Okay, I'm going to need another one of these guys down to go down. Okay, and light off, and if the answer is yes, I'm going to keep going. So I'm going to have to, these guys say it's just, maybe I could, if I like, I can put yes, or I could put just true. Because it's got to be a true, false question. So if this is true, light is off. Then I will continue this way. If it's not, I'm just going to, maybe I'll just keep checking. I'm not going to even wait. I'm just going to keep checking again and again and again and again, like a crazy person. Okay. I'm not that patient. Okay. So he's going to just do this little loop here. Okay. Assuming the waffle iron is hot, then I'll be able to start dumping my batter on, but I have to make sure it's already folded. So this guy, I would say I need to basically, this is going to be able to come back somewhere down. Everything has to be folded first. So I'm thinking this may, it's a little bit awkward the way I've done it right now. So I may have to, I'm going to have to change this a little bit because this does not look quite right. So I'm going to move him up higher, give me a little bit more room. Okay. Because this is not the way I want this bar to go. I'm probably off to have, I probably should better put another bar right here. So that my heating is totally separate. Now I can put my closing bar here. It doesn't matter the angle. So my closing bar can be sideways because I don't have enough room for here. Okay, my closing bar will be there. So folding, if I finish my folding, and I've got my batter ready, and my waffle iron's ready. Now I can continue on. Now, you don't have to draw it like this, but this sort of gives you an idea on what different people can do. So if you had more than one person working, you could have one person working on heating up the waffle iron, one person mixing the dry, the other person worrying about the wet stuff. Okay, so we can see how different people can work together. Now we can put the thing on. We've got the hot things folded, and we start cooking. Okay, pour on, pour batter, okay, and after that we want to check when the steam stops coming out of remove and eat. Okay, so I'm going to have a decision box. And probably I'll put a comment. Steam. And if there's steam, what am I going to do? If there's no steam, what? Okay. Need this arrow again. And this will be, I'm going to probably make this, if I keep going, it's got to be a false. So, okay, if there's no steam, then I can keep going. If there is steam, it's a loop again. So that means I've got to get myself back in again. So I'll do another one of these little loops. Come on, loop. Be nice. There, this guy, go to here. Good. Okay. False. There's no more steam. Then I have a few steps. Remove. And my final step will be to eat. They're separate actions. Actually, removing and eating are separate actions, so they should be separate boxes. And finish. So I need this little arrow. Okay. If there's any questions, you can ask the TA, but basically, I think we'll finish now for today. Thank you very much. Sorry we're a little bit late. Please hand in the milestone sheet for your attendance record. Hand in the milestone sheet to the TA for your attendance record. Thank you very much. Bye-bye.